Hello everyone, welcome to Course Edit. So today we will be uh, learning about connected components and graph. So first we'll be doing for undirected graphs. Then later we also know that there are directed graphs in which we direct nodes from one to another, from one node to another. And in directed graphs, when we go, we'll be learning about two types of connected components. So first let me write the topic and then explain to you what I mean by that. Okay, so first we have connected components for undirected graphs. So for undirected graphs, we have like the normal stuff. We'll be using DFS to solve to travel everything from one to another. And then when we want the next index, we'll be just checking it in the for loop uh, for for all the nodes. So basically your n will be the node. Now suppose if the n goes above your n goes above something, like it goes to 10 to the power 8, then you might not be able to solve it using DFS or BFS either. So for now we won't be talking about that. For now just think about strongly connected components as a normal step in which you will be just solving for less than equals 10 to the power 5. So you don't have to worry much about that. N is less than equals to 10 to the power 5. It is the general case for any competitive programming website such as Codeforces or AdCoders. So you don't have to worry much about that. Next, what we have is we'll be checking for every component whether we have already visited that component or not. So we'll be checking for each node. If this node, which is I equals 1, if visited I, then we will continue. Otherwise, if it is not visited, else we will, or you can directly say, if not visited, then we can just write the code. So we'll be doing the DFS over here if it has not been visited. So what I want to say is, suppose you have a graph in which you have separate graphs. For one you have 1, 2 and 3, and for the next you have okay, so we won't be taking cyclic graphs because DFS will might fail. Okay, so where was I? Yeah, so I was for 1 to 3 you have this, and then for 4, 5, 6 they are not connected by anything, but they are the part of graph. Basically these are called connected graphs when they are not connected by anything, but they are the part of graph. So basically you now know that when do we use them. So basically if you have a user like user 1 and you have to store the data for them, and you have a user 2, or you can say in AI you have like a push, or you can say the randomness of learning. So basically if you have a push, so a push is stored in this a push 1. Basically the learning first thing your AI learns is stored over here, and the next thing that your AI learns is over here. So for both you'll have the push as counting, but you want the data to be separate, so you won't be connecting anything with this to this. Basically it won't be 1, 2 or 3, it will be the data inside this. I'm just writing that as 1, 2 and 3. So you have these two things. Next what you can have is basically there can be multiple more non-connected components. Basically they won't be connected by any edge. So basically these are some examples of connected components. Next you have directed graph. So basically directed is actually used in AI only, or you can say even in CPUs. If you want to make a better CPU, you can use directed graphs. Well, but mostly graphs are used by Google in their maps. That's a major, you can say, application of graph. So directed graphs are basically whether you want to go from 1 to 2 or you want to come back. So suppose if you want to go 1 to 2 to 3, but you don't want to come back, or you want to take the shortest route some other way, then you'll have like uh, in Google Maps or any maps, you always have directed graphs like this. And next, what you can have is example of a directed graphs as like connected components. We have like two examples, or you can say two types. We have a strongly connected components, and next we have weakly connected components. Okay, so weakly, well, basically these are powerful, these are weaker than strongly, or you can say it's just a name because it was given it like this. Though in my perception, you can say that these are stronger ones and these are weaker ones, because these help a lot and these doesn't help much. So it's all according to your perception, whatever you want to call them. But yeah, strongly connected graphs are basically like each vertex can reach every other vertex following the direction following the direction of arrows So basically what I want to say is basically this is an example of cyclic graphs. Obviously you can only return either in undirected graphs or if there exists a cycle in directed graphs. Basically from 1 to 2 you can travel from 1 to 2, but you can't travel from 2 to 1. So basically you either need a back arrow for that, or you can have like another route for that, which is something like from 3 to 1. So from here you can travel to each and every you can say vertex from any vertex. Suppose you want to go from 2 to 1, you will go from 2 to 3, then 3 to 1, which means you can travel from 2 to 1, and also from 1 to 3 you can travel, and similarly you can travel all the way to each and every node from any node. So that's what this strongly connected means. And weakly connected, you just have like if you turn all the directed arrows into undirected edges, the resulting pieces are weakly connected components. So basically like this, if you make a vertex A and B like this, then it becomes a weakly connected component. So basically in maps, I believe we use strongly connected because sometimes there are one way but not two way. So like you have a map in which like one way road, and then you have to go some other way around, and then you have a different route for coming back over here from A to B. So that's the reason in maps we use strongly connected components instead of weakly connected. But yeah, you never know that there can be also a mixture of both. So like there can be a mixture, but that will be called strongly connected only, because if any of that graph doesn't have like undirected edge, then you can say that you have graphs for both. So basically strongly connected is the correct term for Google Maps. So this will be helpful for your Google Maps or other maps, whatever you want to say. Next you have like the code for this. So for now we can just leave the directed graph code, because I'll be teaching the directed graph code maybe after 6 to 7 lectures, because we haven't reached the directed graph yet. So first we only need to do undirected graphs. So over here we can just have algorithm. So first let me explain the algorithm behind that. So basically at first you are given some 1, 2 and 3. Okay, so this is your undirected graph. What do we say? Undirected graph, and this is the connected component with that. And suppose someone asks you like there is a question. So there is a question which says, how many islands are there, or you can say how many islands are there which has like 3 pools or whatever you can say, 3 sites on which you can travel freely. So suppose if this had the value of even, then we can say for every even the site is, for every even node site is reachable or free to travel, free to travel, requires pass. No, sorry, not this. This is also even. Odd requires pass. Requires pass. Okay, so you have like this. So basically you have even and odd. So it requires pass, and even doesn't require any pass. It's free to travel. So how many total islands are there which has like free sites to travel? All sites are free to travel. All sites are free to travel on how many islands? So suppose if this was your question, well, this will be your homework question. So at first you can like solve the normal one. I'll be giving the code for this in the comments. So go for, so comms, you will be getting the code for this in comments. So next you have like the normal code. So first you will have to write the DFS for how much you can travel from one node to another. So suppose if you are given 1, then you can travel up to 4. Sorry, not up to 4, up to 3. So everything will come 1, 2, and 3. Next, what you have is you'll have to find the use the DFS on 4, which will give you 4, 5, and 6. Next, if there was some more, then you might have more DFS. So for that, what you can do is you can first write normal DFS code. So normal code, normal DFS code, and then what you can do is then you can basically use the for loop for int node equals 0, sorry, not 0, 1, node less than equals n, node plus plus, and then you can have like DFS node, DFS and node if node was never visited. So this will be your uh, final takeaway from the code. So basically you will be having a visited node, or you can say visited array, in which you will be storing your data, where you will say that nodes are basically traveled or not. So if they have been visited, then you won't be calling the DFS. If they have not been visited, then you'll be calling the DFS. So let's write the code and then you'll understand gradually that. So first you'll have to analyze the code yourself. Then you must be able to understand each and every code. If you analyze thoroughly, then you will be able to actually get what I'm writing. So first I'll be writing the DFS code. Let me write it first. Okay, so let me pause, or you can just see what I'm writing and then take how I think or how I solve the question. So at first what I will do is I'll take the node, which I already told you that we need a node. So int node, and then second we need a vector. Second we'll need a vector of visited nodes. Third we'll need the graph. And then what we can do is we can basically use the recursion to solve RDFS. So what we'll be doing is, okay, so basically we'll be just checking the visited node. Visited node equals true if it has not been visited. And next what we can do is basically we can call for each and every connected nodes with that for auto non-visited node, or you can say connected nodes. So basically I'll be writing that as v. And then what we can do is we can basically, if v visited v, if not visited v, then we call for DFS, which will be v and visited and graph. Okay, so since we later need this or always need this to like update itself, so we'll be using ampersand symbol, which is call by reference, as I've already taught you. So if you haven't yet read about that or learned about that, then you can go to the pointers video and then you can check how I called them. Basically it was lecture 10 or something like that. So if not visited v, then DFS has been called. Okay, so this looks good. Or okay, so we can also like, okay, so we'll also need a, what do we say? We'll also need some current push. Okay, so we'll be also taking a vector in which will be like, it will be the vector and current, or you can say connected components. So current, so instead of current we'll be writing connected components dot pushback, and then we'll be pushing the node in that. So this is it for now. So not just this, but we'll also be taking index, basically index for this one. What do we say this? For connected component, we'll be taking the index. So I'll be doing this. So for each and every like whatever we need, we'll be doing this. So I'll be creating an instance of first index, and then I'll be creating the index instance of each node in that. So that will give us the perfect pair we need. Okay, so next we need, okay, so we can, well, this index looks good. Okay, so next we have in 10 commands. Okay, so what we are doing here is basically we are just taking every node, and then we are just taking the input for now, and we are inserting, since it is an undirected graph, so we will be using, we'll be inserting for both the index. Well, basically if you have like watched the previous video, then you should be able to get what I'm doing. Okay, so next we have like this. Then what you can do is you can just call for DFS. Okay, so first you'll have to check whether it has been whether it has been visited or not. So if visited node, then continue, or we can just directly do if not visited. So basically this symbol is not, if you don't know, and this I have already explained about this in previous lectures, so please go back and learn everything, then only come back. Okay, so what I was saying is if not visited, then you can call for the DFS. Also what you can do is you need index 0. Okay, so we don't need any index over here. What I can do is, okay, so we do need index, but it's like you don't actually need it completely. So like we'll be calling the DFS, and then we'll also be incrementing the index. And what else we'll be doing is basically we will also we will also like insert a different segment for different nodes for different components in connected component. So how we can do that is basically we can just create an instance by writing this connected component dot pushback, and we can keep this as empty. So this will create a different instance, and then we are good to go with this. So I need to do this first, and then we can over here, and then it will be good. Okay, so now we have like just left with this. So node is node, and then we have visited. Also we have graph. Since we don't have to do any changes in graph and we want to store that, so we are not using ampersand symbol over here. Okay, so here we need that. So basically here we'll be adding ampersand symbol in connected component, and we don't need that in index because we are storing the index over here. Well, you can, if you want, you can do it over here, and then you can just add the index over here. But no, actually you can't. You have to do this over here. So yeah, so you have to do it like this. Connected component, and then what we have is index. Okay, so this should be completely correct. Let's first check what we are getting. For auto component, then what we have is basically we have like vertex or node, we can say node is to component, then you can see out node. So basically this is it. So we also need an example, so we'll be taking the normal example 1 2 3 and 4 5 6. So how many? 6 and 6. 1 2 2, okay, 2 3, and then 4 5 5 6, and also 4 6, and over here we have 1 3. Okay, so this should give us the result as 1 2 3 and 4 5 6. So over here what we can do is, what we can see out is basically component component number over there, and then we'll have like everything we need. Okay, so now we should get the answer correctly. We should get 1 2 3 and then 4 5 6 for component 2. Okay, so we just added few more things, so we need to change this. Connected component and then index. I believe we are good. Okay, so to like create an instance of vector, we also need to write vector int inside this, and then we can pass an empty vector over here. So passing an empty vector will give us what we need. And over here we have visited, which is not correct or something like that. Node and then visited. Okay, so this was supposed to be bool, not an teacher data type. So now I think we are good, or maybe there are some more errors. Okay. Okay, so what's the problem? Okay, so over here we didn't like end the sentence. Yeah, so now we are getting the correct answer. So let me just give a quick recap for this. So first we write a normal DFS, which is, and we also store connected component over here. And for every connected component, we are taking the value in the index and we are amplifying or you can say changing the index over here. And for every, to create an instance for every index, every new index or every new component, what we are doing is we are basically pushing empty vector. So basically this is an empty vector which we are pushing in connected component to create an instance. Since this was an complete empty vector of vector, we created a vector inside that which doesn't hold any value for first index. So that creates index 0, and then we have something for index 1, index 2 and index 3. So like you can just do some research on this by writing few more codes based on this connected component dot pushback vector int, and you can just write your own question. Well, basically there was one more question which I told you. You can try practicing that and you will get the complete grasp on what I'm telling you. So basically all sites are free to travel on how many, so you have to find basically how many islands are free to travel, such as their all sites are free to travel. So let me write the question first. So basically you got this one, right? So now you don't have any problem with this. So next we have question. You, or we will be just solving the question tomorrow. You can just try solving it tomorrow itself. So tomorrow will be the question day. So thank you everyone. Thank you for watching. Thank you.